Hello everyone, my name is Vineet. Today we'll be discussing about the interconversion between push-down automata and context-free grammar. Our aim is to establish the equivalence relationship between PDA and CFG, and in order to do so we have to prove that given a PDA we can convert it to CFG and vice versa, that is given a CFG we can convert it into its equivalent PDA. Now these conversions are very simple, we just need to follow some steps. So without a further ado, let's get started.
Yeah. So before starting with the video, let's actually go through the terminology. So here are a few simple things. I think you might already know all of these things. Terminal symbol. Terminal symbols are actually represented by small alphabets, and these are the symbols which cannot be further divided. And they usually occur at the leaf node in the derivation tree. Examples can be small a, small b, small c, and so on. And what exactly do I mean by derivation tree is, let's say we have S giving rise to A, capital A giving to a, small b. So we can parse it from left to right, top to bottom, and the yield of this thing is called A, and B. Alright, so these are called the terminal symbols, and this capital thing which doesn't occur at the leaf nodes are called the non-terminal symbols. Alright, so non-terminal symbols are actually denoted by capital things, and the most important thing to note here is that we can't use numbers to represent non-terminal symbols. The only thing is capital letters are used, and most commonly this capital S is used to represent the initial state. That's basically convention. It's not compulsory to follow this particular thing, but it's a convention to follow this. Alright, now the most important thing is, like I have just shown, like if I have a derivation tree like S, A giving rise to A, B, and if I have, let's suppose, B. Now if I have to parse, it will parse from left to right, top to bottom, but now the parsing will stop only when it encounters a terminal symbol. But here B is a non-terminal symbol, so this is actually not valid. That means B should also be deriving something. That's why it's called a non-terminal symbol. Let's say B derives a single thing B. Now this B becomes a terminal, and we can say the parsing is completely over. So when I say yield of this particular derivation tree, I will say A, B, B. So we can see that it starts with a terminal symbol, it ends with a terminal symbol, and that's how the parsing gets complete. So here we can see that in the string or yield of a grammar, non-terminal symbols are not allowed, because non-terminal symbols will actually eventually give rise to the terminal symbol itself. Hence the parsing of derivation tree is done in such a way that the end is always at the terminal symbol only. Great. Next is context-free grammar. So context-free grammar is actually a grammar which is used to generate all the languages. So we have learned that a grammar is used to generate a language. Alright, and a language is a representation of a set of strings like that follow a particular pattern that is denoted by the rules of the language. Alright, so context-free grammar can be defined by 4 tuples VTPS. So T describes the set of terminal symbols, that is a small letter ones. V describes set of non-terminal symbols, that is the we can say capital A, capital B, and stuff like that. P describes the production rules. Now what exactly is meant by production rules is, we can say like every grammar is written in the form of something. So this arrow is there, that means a non-terminal symbol is deriving a terminal, or a combination of both terminal and non-terminal. This kind of particular thing is called a production rule. Alright, next is S is start symbol. By convention, we always start with S, but it's just a convention. You can also start with any letter that you want. Okay, so far so great. Now next up is the main thing, that is push-down automata. So push-down automata is a finite automata. So I guess till now you might have heard about this famous language L equals to A power n and B power n, where n is greater than or equals to 1, let's say. The reason this language was not accepted by a regular language, because it used to have a dependency between these two things. If n is equals to 8, then it has to be A power 8 and B power 8. So there needs to be some kind of extra memory element needed. That's why we have another kind of machine, finite state machine, that is push-down automata, which has an extra element in the form of a stack, which helps the push-down automata to recognize context-free languages. So these kind of languages are called context-free languages. Alright, so here again the terminology is simple. Here Q is basically a finite set of states. Alphabet is this lambda, this sigma is the input alphabet. This one is called the stack element, which can be pushed and popped from the top of the stack. So basically in stack, I guess you all might be knowing how does a stack look like. by convention, we keep Z0 at the bottom. If I encounter A, I can push A, I can push B, but if I want to pop, so I can only pop the topmost element. So it follows LIFO rule, that is last in, first out. So this is used to, represent the element at the top of the stack. Alright, Q0 is the initial state, Z is a start symbol which is in this one, the stack symbols, and you can say F is a set of final states. Alright, and you can say delta is the mapping, or you can say it's a mapping which is used for moving from the current state or this thing, or we can simply call it a transition rule. Next up is Chomsky normal form. The Chomsky normal form is, they just define a format in which if a particular grammar lies, they can be called to be in CNF. For example, so, a CFG is said to be in Chomsky normal form if all the production rules satisfy one of the following conditions, that is the start symbol. They should either, so simply you can say, if I have any symbol, it can lead to this, or it can lead to a single, you can say a terminal symbol. So that will also work. Or you can say that like any symbol, not just S, if I say capital A, it should lead to a single non-terminal symbol should lead to exactly two non-terminal symbols. So if these two conditions are satisfied, then we can simply say that your particular grammar is in CNF. Moving on to Grayback normal form, it's one step ahead of this thing. Now the only difference is here what we are doing is the first condition, that is, a non-terminal giving to a single terminal, remains the same. But in CNF, you can observe that the second condition was like a single non-terminal state can lead to two non-terminals. But here, the condition is a single non-terminal cannot lead to like this. It has to lead to a single terminal state followed by n number of non-terminals. So this condition is very important. When condition like this is followed, we can say that the given grammar is in Grayback normal form. Alright. Next is, you can say the equivalence between PDA and CFG. Now the reason why we are doing this is because we want to make sure that PDA and CFG are equivalent. So what we do is, so the equivalence can be established when we can prove that a given PDA can be converted to context-free grammar, and also a given context-free grammar can be converted back to its equivalent PDA. If these two conditions are satisfied, then we can, safely, conclude that PDA is equivalent to CFG. All right. So we'll be dealing off with the part one, which is like conversion of context-free grammar to PDA. Now the problem statement is very interesting. It's given the production rules of a CFG, we need to construct its equivalent PDA. Now there are 5 simple steps, step 1, 2, 3, 4, 5. That's it. If you follow these 5 steps, you will be able to, convert a CFG, that is context-free grammar, into PDA. Let's quickly get on to step 1. Step 1 is you have to convert the given production of CFG into GNF. That is, you have to ensure that all the non-terminals yield either a terminal or a terminal followed by n number of non-terminal. This should be the format for all the production rules. If all the production rules are in this format, we can say that our first step is done. Simple, right? So we have to ensure that the given production is in GNF. So yeah, this is what we have just discussed. And if you want to know exactly, then you can go back to the terminology section and see how exactly the rules are being defined. Now, the important thing to note is whenever the grammar is in GNF, we can say that the corresponding PDA will only have one state. Alright. So, step number 2 is the PDA will only contain one step, and we are taking just Q for right now. That's simple. Now, coming on to step 3, this is very important. And it's very logical. You can see the initial symbol of the CFG will be the initial symbol in PDA. And why do I need to consider initial symbol? Because of initial symbol only, I'll be able to make the derivation. For example, S tends to A, B, B. So I need to have this initial symbol. This is called the initial symbol. All right. Yeah. Next up is, the fourth step is, for non-terminal symbols, you have to add the following rules. So we know that non-terminal is like capital letters. So whenever you encounter a capital alphabet, you have to say that delta of Q comma epsilon comma A gives rise to Q comma A. So this is basically read as the in PDA it will be read as the current state is Q, the input symbol is sigma, that is nothing, and at the top of the stack you obtain capital A. So in that case, you will make a transition to another state Q in which A will be there. So yeah, now this will be occurring. How does this thing occur? This will occur when we have the production rule of CFG in the form of capital A tends to A. So A will be placed here and this A will come here. Again, like since we have defined for non-terminals, we will also define the same for terminal symbols. Now for terminal symbols, we have to like this. So terminal symbols means small alphabets. So for them, we'll be saying delta of Q comma A. For example, if I have two terminal symbols, let's say A and B. For A, I will write delta of Q comma A will give to Q comma epsilon. Epsilon means it's a pop operation. For similarly for B, I will write delta of Q comma B, I will give Q comma epsilon. Great. So far, so great. So now the steps are officially over. Now, once this thing is done, let's take an example to quickly understand how these things are working because it is very simple. For example, you have this kind of a grammar. Like these are the production rules like S tends to A and A tends to AS, BS or this. Or means like A can derive either one of the following at a time. Alright. And that can be anything. So basically the first step is we can say that the set of the terminals is AB, the set of non-terminals is AS, initial symbol is S and production rule are these all are the production rules, right? So by this we can say that this is actually a context-free grammar. Now next up is we need to convert this context-free grammar to its equivalent PDA. So following those 5 steps, let's quickly summarize the 5 steps and let's see how we can solve this. Step 1 was actually to observe all the production rules are of the form A gives rise to either a single terminal or you can say a terminal followed by n number of non-terminals. Now we can see like here S is like single terminal followed by 2 non-terminals, single terminal followed by a single terminal and single terminal. So this means that this is already in GNF. So that's really great. Second step is the PDA will contain only one state, that is Q. So we have taken Q as the state of the PDA. Third one is the initial symbol of the CFG in S will be the initial symbol in PDA. So for that, I need to make a transition and a PDA is actually defined by its transition. All right. So I will say that delta of Q comma epsilon comma S will be instead of S, I know that my production rule was S gives rise to A. So I will actually keep instead of this initial symbol, I will give A. Alright, now for each non-terminal, you have to apply the rules. Now here I only have one non-terminal that is A. So I will apply this rule for this. So I've kept Q, epsilon and A instead of A. Now I have seen like A derives, you can say AS or BS or A. So I have to define all of them. So Q comma AS, then Q comma BS, then Q comma A. So I have defined 3 possibilities. And now the 5th step was, it's very simple. For each terminal symbol, apply the rule, this one. Now, here we have 2 terminal symbols, that is A and B. So I have to apply this rule. So Q, A and A. That is whenever the input element is A and at the top of the stack we have a, we do the pop operation. And similarly, whenever we have input of B and at the top of the stack we have B, we do the pop operation. Pop means we are taking out the element from the top of the stack. Now, what we can say is, hence we finally obtain. So if I take into consideration all of them together, so 1, 2, 3 and 4, these 4 together are the, you can say the transition rules for the PDA. Now you might be thinking it's over, but let's see. Sanity check is something which is very important. How can you conclude that the PDA that you got is correct or not? So after opening the PDA, we need to test it on the string generated by the given CFG. If that string gets accepted by the PDA constructed by us, we can safely conclude that the constructed PDA is the correct equivalent form of the given CFG. Testing. How do we do the testing part? To confirm whether the constructed PDA is correct or not, we will test it on a language generated by the CFG. This can be achieved using the derivation tree. Now, let's say this is the derivation tree that we are looking into. S gives rise to A can be AS, S can again give A. Each A is given by AA, and here also we can just take single A. Alright, now if I do the parsing of this derivation tree from left to right, top to bottom, so I will follow the zigzag order and I will get A 6 times. Alright. Now this is one possible derivation tree, but just to take one example which contains both A and B, so I have taken another derivation tree, and after parsing that I get a yield of this thing AB and 4 times A. Now let's actually consider this string. So this string is, generated by the context-free grammar. Now, if I'm able to accept this string by my thing, my PDA, I will say that the PDA that we have derived is correct. So always start with the initial symbol first. If we encounter a terminal symbol at the top of the stack, we can pop it. If we encounter a non-terminal symbol at the top of the stack, we can substitute it by its most appropriate derivation based on the input symbol. So here we have A, B followed by 4 times A. Alright. So AB followed by 4 times A and S. Instead of S, I can substitute A. And here we can notice that A is in the input alphabet and also A is on the top of the stack. So we can actually pop A and A. So when A gets removed, so I get BAA. Now this is a non-terminal, so I need to take it in derivation. So A can give rise to AS, BS, and A. Since we are seeing at the top of this, input is B, so I will take this derivation because this derivation will not make any sense. So instead of A, I can substitute it with BS. So this becomes, instead of A, I've put BS. Now this B and B can be popped. Right. Now I will be left with 4 times A and SA. Now instead of S, I can put AAA because S has only one option to go with A, and A. Now just a second. Yeah. Now once I do that, this A and A, I can pop this thing. Now I'll be left with 3 A's. Now first A can be used to give single A. Alright. Now I'll be getting single A, and this single A and single A can be popped. Now I'll be remaining with 2 small a's and 2 capital A. We know that for A, we can always derive a small a. So instead of substituting, I'll substitute A with small a. This A and this A can now be popped. And if you keep repeating like this, I'll be left with this particular substitution. Now if I substitute capital A with a small a, so I can see there are 2 terminals and both are same. So I can do a pop and I'll get epsilon. This proves that the input string is completely, passed by the given PDA. So we can say that the constructed PDA is the correct equivalence of the given context-free grammar. So by following the above mentioned 5 simple steps, we are able to convert a given CFG into a PDA. So that's it. Now we'll be looking into how do we convert a PDA to CFG. So let's quickly understand how do we do the reverse, that is PDA to CFG. Alright, so given a pushdown automata, we need to create its constituent CFG. So there are 3 simple rules. That's it. We just need to formulate the, you can say the production rules given the transition rules. So first is like the S production, that is the initial state production is given by S tends to, you can say Q naught, Z naught, and Q. And here Q will be belongs to all set of Qs that we have. Alright, now for every popping move, let's suppose we have the input state as Q and then we have the input symbol as A and at top of the stack we have Z. So it will give rise to Q dash, that's a new state. There's a transition to new state, and also epsilon. Epsilon means it's a popping move. So here what we are going to do is you just need to observe the pattern. That's it. You just need to know where do I place it. Placement is very important. Q will be kept as it is. A will come here and this Z will come here in the middle, and this Q dash new state will come here. So this will actually constitute a, you can say a production node. For example, you can call this as capital A. Then in CFG, we can write this as A tends to small a. Cool. Now for every push move, since we have popping moves, we have pushing moves also. For every push move, there's a like A and Z. If you are pushing a lot of elements, there's a transition to a new state Q1, and then you can see Z1, Z2, Z3 up to so on. Now here also you can see this particular thing is very easy. Q will remain as it is, A will come here, Z will come here, this particular Q dash will be there. Now this Q dash will also be there at the last, okay. And also like if we have Q1, Q2 and so on, so Q1 will be there and Q2 will be there, and this Q2 and Q2 will match, this Q3 with this thing will match, it will keep on going like that. So there's a pattern that you have to follow, and we'll look at an example to thoroughly understand how these things work. Okay. So if we follow these 3 particular steps, we can easily derive the production rules for the equivalent CFG. Now, for example, if this is the PDA being given, so we can see that there are 7 transition rules here. There are 2 states, that is Q0 and Q1. So, and also there are 2 elements like X and Z0. So let's see how we are able to convert each transition rule into its constituent production rules that we need in CFG. Solution is very simple. We can say that let's consider the S production first. Since we have two symbols, that is Q0 and Q1. So first, initially we'll be going with Q0, Z0, Q0. These two will be same. Now we'll be going with Q0, Z0 and Q1. All right. Now, if I take this particular thing as A and this particular thing as B, I can safely say it's almost equivalent to S tends to A slash B and this will be a a production rule in context-free grammar. All right, that's great. Now let's actually take into consideration all of these transitions. So we can see like this Q0 1 Z0 and this Q0 X Z0. We are pushing something. It's a push move. So we need to apply rule number 3. Now we can see like here there are two elements, that is X and Z0, and there are two states Q0 and Q1. So there will be a total of 4 productions. Let's actually notice the pattern. So let me just copy that particular thing here. So delta of Q0 comma 1 comma Z0 gives Q0 comma X Z0. It's very simple. Q0 will be at the first position of all of them. All right. Then we'll be placing 1 here at the start of all of them. Okay. Z0 will stay at the middle. So you can say Z0, 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 Z0. And let's actually see how do I fill this. Since we have Q0 state here, so again I will fill all of these Q0s first. So we need to just observe the pattern. All right. Next up is Z0 is, now we have two elements, that is X and Z0. So I'll write X, X, X in the first one, and second one is Z0. So I'll say Z0, Z0, Z0 in the middle. If I have something else, I'll make another ones and I'll keep Z1, Z2, Z1 and so on. Next up is, now we need all possible combinations. So I have two states only, that is Q0 and Q1. So I'll write Q0. So I'll write Q0, Q0, Q1, Q1. So as to cover all this. And since I have written Q0 here, so it will also be Q0. Here also Q0, so it will also be Q0. Here also I have Q1, it will be Q1. And here I have Q1, it will be Q1. And now these two are remaining. Just take all the combinations. Q0, Q0, Q1, Q1, Q0, Q0, Q1, Q1. Now these set of 4, you can say these are the production rules for the given grammar. So that's very simple. You just need to know where things are going. That's it. All right. Let's move down. For the second transition, it's also a push move, so we can apply the same thing again and you will be able to get the result. For the third thing, let me just solve this one because this is a bit thing. For third thing, it's a push, and since we have only one element, so we just have only two combinations, one value in the stack and two states, so two combinations. Q0 will be kept as start, so Q0 and Q0. X will come towards the middle, it will become X and X. We have to take all combinations, so first Q0 and then Q1. 0 will come here, so 0 and 0. Q0 was there, so we'll keep Q0 as starting, Q0 and Q0, and then X will keep X and X, and if it's Q0, it will be Q0, and if it's Q1, it will be Q1. So sorry, it will be Q1. Now, next thing is, for the fourth transition, it's a pop move. For popping moves, it's very simple. Again, what you need to do is, you have to just see if it's a Q0, it will become Q0. If it's an epsilon, it will come here. This X will come to the middle and this new state will come here. That's it. A single rule for a pop. So that's really simple. Now for the fifth thing, it's again a pop move. So again, you can follow the same steps. Q1 will be here. X will come to the middle. Q1 will be here. This epsilon will come here. Single transition, or you can say production rule for the CFG. Now for the sixth one, it's a transition move. Again, 2 are there, the 2 into 4 will be there. Similarly, you can keep filling this thing. Now for the last combination, you can see it's a pop. So again for pop, you know that Q1 will be here, this X will be there, and then 0 will come here, and this Q1 will come here. So that's how these things work. So this will result into a single production. All right. So finally, we can see like, so for all the 7 transitions, we have obtained a lot of production rules for the CFG. We need to determine like some productions are repeated. All right, so they are useless productions, so we need to remove them. Also, you can further convert these productions into a compact form by removing all the null useless productions, removing null productions, and removing useless, you can say unit productions. So that's it from my side. Thank you so much.